Okay, let's say, how many of you guys know how to make a cheese sandwich? Basic cheese.
Oh, mine's not basic, but it's excellent.
You do? Okay, so let's say we're making the basic cheese sandwich ever, right?
Boring.
Is that the real cheese?
Get it away
Real
from me.
cheese,
Don't
yes.
want it.
Yeah, cheese.
Did you get it? What?
Okay, let's say we have 20 slices of bread, chapter 10. 20 slices of bread.
All my stuff that was in my bag smells like incense. It's like vanilla-ish.
And we have 7 slices of cheese. Now, we know the recipe for a cheese sandwich is 2 slices of bread,
Garlic butter, bacon, jalapenos.
really good.
Yeah. Yeah. Start over.
Plus 1 slice of cheese. And then that's going to yield 1 cheese sandwich.
I can have 20 slices of bread and only 7 slices of cheese. That doesn't even make sense.
Oh my gosh.
Are you gonna cut it in half? Okay, 2 slices of bread, 1 cheese. Those 10. So what's in 3 slices? Is it broke times? Do we have to cut the cheese out?
Some riddles. Okay,
Oh, 8 can't.
So- how many complete sandwiches can we make?
You don't want my answer.
You can only make 7, right?
Yeah.
Okay,
But
so, no but, there's no but. You can only make 7, right? So what is in excess? Your bread is in excess. So what is limiting? The cheese. Okay, now you've just been introduced to limiting. Right, you know the cheese is limiting. So the moral of the story is you can only make as much as you have, right? So if you're missing one of the reactants, or one of your reactants are really low, you can only make as much to that lowest reactant that you have. Does that make sense? And that's, again, it's going to be based upon, they're going to be based upon mass, or they're going to be based upon quantity. It's going to be based upon quantity.
can you say that last
Think so.
sentence again over the, you can only make as much as you what?
As the smallest quantity that you have.
Okay.
Okay. Does that make sense?
Yeah.
So now this applies to chemistry as well, right? Not just cheese sandwiches. So if we have 3 carbons
That's fine.
and we have 2 oxygen gas, and we're making carbon dioxide, how many carbon dioxides can we can only make 2. That is correct.
I want to repeat.
And so you guys can see that in this this graphic here. We've got 3 carbon, we've got 2 carbon dioxide, so we're only able to make
Mine and hers are
2 carbon dioxide. Oxygen, sorry about that. Only we make able to make 2 carbon dioxide. So we have 1 extra carbon. So the carbon is in excess and the oxygen is there. Okay. So the very first thing that we want to do is convert these to moles. Guys, it has to be based upon quantity. So again, moles is our gateway drug. That's going to take us to where we want to get to moles. Okay, once you get to moles, there's a couple of ways of getting to the answer. One of them, we can actually do the calculations with both of your reagents, because typically you're gonna have, you're given two reagents, one of them has to be limited, or they're gonna be exactly the same, or they're gonna end up being the same. But by calculating the number of moles, you can kind of figure out which one's limited. You can take that as your starting point and get to the end, or what you're gonna have to do is you're gonna have to compare apples to apples. What do I mean by comparing apples to apples? So if I have the moles of, let's say we're talking about the carbon and oxygen. If I have the moles of carbons and the moles of the oxygen, I can compare them to each other by converting the other one to how much I would produce, or how much I would need to produce our product. Okay, so let me give you an example. Okay. Here it says calculate the mass of Anthony 3 iodide, Sb, that can be produced by the reaction of 129 grams of anthony and 381 grams of iodine. So what is, first off, what would be the chemical reaction?
SB plus I goes to SB.
Sb plus I. Okay, is there something that we know about I? Diatomic, so it should be I2, right? And then that's going to go to Sb I3. You guys seeing that? Is it balanced? Or do we need to balance it? There and there. Okay. Okay, now is it balanced? Okay. So now that we have a balanced chemical equation, we need to figure out the number of moles of anthony and the number of moles of iodine. Okay. So 9 grams of anthony. How much is anthony? What was that? That Z equals 151 is the atomic number. Z represents the atomic number. So 121. Okay, that's going to equal okay, the iodine, 381 grams. What is the molar mass of iodine? It's 1 times 2.
Thank you.
That's good. Zero, because thanks, right?
Yeah.
Okay, so now they're both in moles. So one way of determining which one is limiting is this is what we actually have. And we can figure out how much we're going to need if we reacted all of this by doing a comparison of the number of moles of anthony. The way that we do that is we'll go a little bit further and we'll do the mole to mole ratio of anthony to iodine. For every 2 moles of anthony, we have 3 moles of iodine. Why do we do it in this order? You don't have to do it, well, you can do it in either order. You just want to compare the two, right? So this is how much iodine we actually have. This is how much we need. Okay. So this would be 1.5. Okay, so as I said earlier, this is what we would need. And here, this is what we actually have. Need to have. So in this case, since we only have 1.5, 1.50 moles of iodine, and we would need 1.59 moles of iodine to react with all of that anthony. Which one is that? The iodine. The iodine is limited because it's smaller, right? It's smaller than what you actually need of the iodine. So do you guys understand what I'm saying about comparing apples to apples instead of comparing apples to oranges? So I can't just look at the anthony and the iodine and make a decision which one's limiting. I have to change to figure out how much, if I use up all of my anthony, how much iodine I'm going to need to react with that anthony. Then I have to compare that iodine to iodine.
You gotta run out of answering.
No, I'm going to run out of iodine because I only have 1.50 moles of iodine. And then if I reacted all of the anthony, this chemical reaction, what was that?
You can have iodine.
I'm not going to have iodine. I'm going to run out of iodine. This is how much I'm going to need for a complete reaction with all of the anthony that's present. Okay, so remember when we're talking about the cheese sandwiches, right? So the ratio was a 2-to-1, 2 breads to 1 cheese, right? What was that?
I was seeing something like this, understanding why it was comparing, like you said, it's a 2-to-1.
Mhm. Yeah, because the chemical reaction is, we have the ratio, it's 2 to 3, right? So for every 2 anthony's, I'm going to need 3 iodine. Okay. So I use my ratio. My ratio tells me here that if I use up all of my anthony, this is how much iodine I'm going to need. Right? So it says I need 1.59 moles of iodine, right? So give me 1 second. Then, but I only have, because I calculated what I actually have, this is the amount of iodine I actually have, grams. When I convert it to moles, there's only 1.50. Isn't 1.59 greater than 1.50?
Yes.
So then that means that what I have is limiting compared to what I need. Okay, does that make sense? Because here, this is how much anthony I have, right? So if I use up all of my anthony, this is how much iodine I'm gonna need to react with.
That number was lower than 1.5. You know,
Then that means
and space
the limiting. Because here, this is why it's important to distinguish. This is what I actually have, right? Here, this is the anthony that I actually have. Now, if I react all of my anthony, this is how much iodine I would need to react with all of that anthony. Okay? Okay, so again, it's like those cheese sandwiches. Only had 7 slices of cheese, right? We had 20 slices of bread. So then which one would be limited, right? Okay. You guys see the relationship?
And where, how do we know that one goes first?
No, it doesn't matter. I could have started with the iodine, right? And then I could have worked the other way around. I just happened to put anthony first because I did my calculation for anthony first. It was the first one that was given to me, right? Okay, so this is one way of figuring it out. The other way of figuring it out is just by, and the reason, I'll tell you the reason why I do this. I always try to find the fastest way to get to the answer. Because at the end of the day, time is money, right? So you always want to figure out the fastest way to get to the answer. So I read the question and I try to figure out, okay, what is the fastest way of getting to the answer? Yes, and the fastest way is comparing these two to each other, right? What I could have also done, I could have just did the case where I just went from anthony and figured out how much of my anthony 3 iodine I made for both cases. So that's figuring this all the way out for how much I made for this, and figuring it all out for how much I made for this one. And then the one that's the lowest value is my correct answer. Okay, so that would be another way to do it. We'll show you that way as well. So to answer the first part of the question, which we haven't done yet. So since we know that the iodine is limiting, we'll start off with that one. So if we wanted to compare, if we know that we already know that this guy is a limiting agent, we would just go the ratio of iodine to our anthony 3 iodine. And that would be 3 moles, 1 mole. Sorry, 2 moles. Okay, so then this would just be 0. You guys see that? Okay. Now, if I use this, so I go 1.06 moles of anthony. I convert that to 2 to 2, so 2 moles. SB 2 moles. SB I3. Gonna end up getting the same answer. Sorry, I put it over here. So that's just gonna be that 1.06. So that shows me again that if I use my anthemine, right, I'm gonna end up with 1.06 moles of SbI3. If I use my iodine, I end up with 1.00 moles. Right. So again, this is the lower value. So I know that iodine is limiting where anthemine is next. So we know which one is limiting. So now we just have to calculate the mass. So we know that SB3. So what is the molar mass of SbI3? So we had what? 7 points. How much does iodine weigh again?
126.
Okay, times 3 plus, anthemine was 121. 7, 6.
7.
Three. Two. Sorry. 502. 6. So, law of conservation says what? What was that?
Calculate organic. No.
Something gaining for nothing? Okay, matter can't be destroyed or created. Okay. So that boils down to what? The law of conservation says what? Then I said, and then he says matter can't be destroyed or created. So then that boils down to what? What was that? The wing?
Wait.
The weight. What do you mean by that? What was that? Yeah, that does mean that it's transformed into something else, but what does it mean? What does it boil down to? What is the simplest thing you get from
Nothing
the law of conservation?
Keep it creative.
Okay, so then translate to me, what does that mean?
No, new matter can be created, but you can't distribute it and change it to another form. So just-
Jack said it differently, but he's saying exactly the same thing that you're saying. Jack, what do you think it means?
Can't lose, okay. That's what Gabriel said.
Okay, so, but what does that mean?
I don't know, but it's like a chemical equation, how you can't change the source. You
Okay,
can
but
add
what
like
did I say about that?
Yeah, add or take away, what don't you have?
What was that?
Kind of add or take away.
Okay, so you're saying what you put in is what you get out.
Yes.
Okay, perfect. That's exactly what I wanted to try to get. So what we put in is what we must get out. How much did we put in? All together, what is the total mass that we put in? No, that's how much we got out of the reaction. Okay, you said 129 plus 381. 129 plus 381. What does that equal? Okay, 510. Okay, so altogether we put in 510. And our reaction was only, what we got out of a reaction is 502.46. So then how much excess was left over? And that would have been of what? And okay, that was that second part of the question. It says also find the mass in grams of the element that was left over. Everybody got it down?
Yeah.
Okay. So the next part that we want to talk about is energy. So does anybody know the definition of energy? That's from the very first part of the semester. What was that?
In a sense.
No. No. Fuel is a substance that contains energy stored. It's general, you guys remember? What up? Okay, so if you do no work for this class, what happens? put no energy into this class, what happens? Fail, right? Okay, so, and you fail because you did what? Did no work,
But no energy.
that's right, you put no energy, right? So work is the capacity of doing. Energy is the capacity of doing work, okay? So that's what it boils out to. Now, the way that we measure energy is, yes, that we use energy, is the joule. Joule is the SI unit.
Like how
And a
strong
joule-
it is.
What was that?
Like how strong it is. Like if this has the most energy, it could probably, like a generator can give power to a building, and this generator can give power to a town type of thing, like that.
Okay,
They have one of this. They have different types of energy, like different amounts of
yes,
strength.
yeah, I understand, you're understanding, yes. So, yes, so it's the ability of those generators to do work, right? Okay, and so you're saying if this generator has more energy, it's able to do. Yeah. Okay, now the units for energy is joules. Joules. Yes, that's for SI. You guys remember SI units? Okay, so now a joule basically is defined as force of 1 Newton applied over a distance of 1 meter. So if I decide to pull him all the way across for 1 meter, right? That force that I'm using, that I'm applying to sit there and do it, that's going to represent. Okay, so the unit for 1 joule is also going to be equal to 1, because he weighs a lot. I'm going to say he weighs more than a kilogram. Right? So 1 joule is going to be equal to 1 kilogram per meters square second square. Okay. Now in the U.S. we don't do that. We don't use that. We use calories. Right. That's how we define energy, and that's just the energy to raise 1 gram of water 1 degree Celsius or Kelvin. So you're taking it by a single degree temperature. Yes, just to raise it. By a single degree. Now the relationship between a calorie and a joule, 1 calorie is equal to 4.184 joules. Okay. So a kilocalorie and a kilojoule and a kilocalorie are often used to kind of make it a little easier for us to write things. So 1 kilocalorie is going to be equal to 4.184 kilojoules. Kilo. Okay. So a food calorie is going to be equal, or a capital C calorie is going to be equal to 1,000 calories, small c calories. So let's say I had chips that were actually cheeses. That's what I used to. I had cheeses that were 100 calories, capital C calorie. How many lowercase calories would that be? Lowercase c calories. That's how many joules that would be. All right, we'll get to that. But capital C calorie are food calories. That's what we see on the back of labels. Right? So you guys have.
Wasn't it based on person?
What was that?
Based on person serving?
Yes, it's based upon person. All right, make it six.
I got some Swedish fish,
What was that?
like candy.
Oh,
Oh,
yeah.
yeah, which one you really like Swedish fish?
Capital C calories. That's right. 1 capital C calorie is equivalent to 1,000 small c calories. We use them in science, right? So when you're actually doing the calculations, we use the small c calories. But nobody wants to think, okay, I just ate 100 calories, right? Small c calories. So we make ourselves feel better by saying, oh, I just ate, 100, instead of saying I ate 100,000 calories. I just had 100,000 calories. Doesn't that make you feel like a fat cow? Right? It makes me feel like a fat cow. I had 100,000 calories. But if I had 100 calories, capital C calories, I just had 100,000 calories, right? Isn't that true? So if I had 100 capital C calories, right? That would be 100,000. I know, it's dumb. Don't worry about it. It throws everybody out, right? Because it doesn't make sense. That's part of the reason why we like this. I like it. Is because we use capital C calories and we use lowercase c calories. So the food industry decided to go with their own set of calories, right? And they actually, this is how it honestly started, right? The person who was doing the calculations fucked up, right? They printed all these labels a long time ago. No, it's true. It is really, really true. Right? Yeah. So, but it was a mistake that they made. And then also because, again, are you okay with having 100 calories? I just had 100 calories. You're okay with that. And then, but if you said you had 100,000 calories, right? That's too many zeros. People start getting freaked out when they start having too many zeros, right? Nobody likes to see that many zeros unless it's after their paycheck, right?
Yes.
Okay. So because of it, right? Because of it, they started utilizing the capital C calorie, right? And then at the same time, we were always using the lowercase c calorie, which means it's the energy that's required, right? Okay, so you guys have to distinguish between capital C versus lowercase. And in most cases, they're pretty good about on nutritional labels. They usually use capital C calories. This is 150 calories, right? Actually, 130. But this one they use capital for everything. Yeah. Capital C calorie, right? Yeah. Okay. So when we're talking about food calories, there's quite a bit of calories when you think about it, right?
Yes.
So that one's capital C.
Yes. Okay. This one here down here for food calorie. So if we're talking about food calories, it's under 60 capital C. Or it has a capital C calorie. If it's lowercase c, right? Okay, so that's a capital C. So then we know that that's 100,000. Okay, so if I just ate 100,000, how many joules was that? If I just ate 100,000 small c calories, how many joules was that? Was it? Said 100? Yes.
Yeah.
So if I just ate 100 calories, that would be 100,000 capital small c calories. Right. So let's just do the conversion. We'll make our life simple.
4.1.
10 to the 1. That's right. That is correct. joules. Okay. Questions? No questions?
But on there,
No, because 1 calorie equals 1,000.
oh, I see.
I know calorie, calorie, and calories, right? So if I just had a burger, that burger was 5,000 calories. It was a big old fat juicy burger. Okay. Then how many, I should say, food calories, capital C calories? 5,000 food calories. Then how many small C calories would that be? If I just ate a burger, that was 5, ready on the board. 5,000 capital C calories. Okay. Then how many small C calories would that be? Okay, so daily allowance, what is the daily allowance of an average adult male? Like,
How many year old?
2,000? Capital C calories. Okay, so then that would be, what was that? I know, it is the stupidest thing, and it drives me crazy, what was that? And it was just like, you had to think, okay, at that point, at some point, you would think that we would decide to change it, right? But that's part of the reason why we go science, if we prefer, because that's how you, actually, that makes more sense. Okay,
Sorry, it's like the actual industry, the typical size uses the.
that's right.
Yeah, the actual.
But once we get accustomed to certain things, right? We're not accepted.
No, it's
Right?
so old.
We got accepted to those capital C calories. You know, we see them on the back of labels, and everybody's like, okay, I'm okay with using it now, right? Even though calorie, don't make sense. Okay, so what I'd like you guys to do is calculate the number of kilocalories, calories, and joules for
It's like right there.
42.5 kilojoules. We're looking for the conversion factor. What was that?
Yeah,
That's 4.184.
It's true. It's repeat.
countless of calories.
They just processing what you said, or they actually-
What?
It's like you tell someone something. It's like, what? Yeah. Sometimes they don't say they heard it. They haven't processed it. But then it's like, wait a minute, yes, they did it.
I could be looking at someone and I'm not listening to.
It could be semi, it could be like semi.
If I'm on my phone, I'm definitely not listening to you unless I'm jumping on the top. But I, for the most part, make eye contact with people when I'm talking to them. So if I'm looking down, I'm probably, if I'm writing down what you're saying, I'm listening.
Yeah.
But if I'm writing something.
Okay,
else
so
down,
how many joules do we have in 4.5? I mean, 4 point,
I thought it was K cal.
42.5.
What are we looking for? I thought we were looking for the K cal.
We're looking for it all, actually.
Oh, okay, 10. 10.15, but they rounded to 10.2.
We have 4.5 kJ, kilojoules. How many joules would that be?
10.2. Wait, what? No,
How many joules?
never mind. I didn't get that. I touched those.
Yeah, ask for joules. So how many joules are in a kilojoule? Kilo, what does kilo mean? Kilo.
10.2. No?
You said so much? 1,000. So we know that 1 kilojoule is going to be 1,000 joules.
Let's go.
That's what you were asking. You're not thug enough to get that view, bro. It's okay.
Okay, now that we have it in joules, what is the relationship between joules and calories, small c calories? So for every
4.184 joules.
4.184 joules.
She's got a tie-dye mask. That's cool.
Yeah, I just forgot to. I know. I graduated from. So
Oh, yeah.
good. It's the first one always bad.
You're not used to the instruction.
It's hard.
But I love it.
Check down.
They're gonna have to have a hard second. Let me finish this and then. Okay.
I'll be around.
Dr. Henry, what she teach again?
Physics.
Physics. That's what she teaches. You're fucking lying. Are you really?
She looks.
She didn't believe me. I told her she's a professor. She's a prodigy.
Okay, so.
Okay, Dr.
one
Kim.
cow. What did you guys, you got 10 point something you said?
10.2 or 10.15, but it rounds to 10.2. What'd you say?
10.15 or 10 or so?
Yeah.
1 point.
10.2.
But that's thousands, right?
Wait, hold on.
You must have did the kilo.
Yeah, I think so. Which one is this? Which one are you asking me for?
This was just calories.
Oh, that's what.
Guys get. What's that?
Yeah.
Oh, like, is it from that? Yeah, sorry. Okay, so it's just like-
It's like a 10,000.
The general thing here.
Yeah, just put it on my.
You're retired.
You're retiring?
Okay. Questions? Concerns? Cash? Kool-Aid? Vote.
How old is your sweater? Why have you questions?
It's like brown, black. It's like.
Okay.
That's how it is.
So
It's like, it took him so long to take off the sticker.
thermochemistry. So remember I told you that when we talked about a chemical equation, we also take into consideration the energy that's associated. So I told you that we would talk about this at this point. So that energy that's associated with that chemical equation is called enthalpy or heat, the heat of the reaction. The way that we symbolize it, enthalpy. Okay, the way that we symbolize it is delta H. Sometimes you'll see delta HR. Sometimes you'll just see delta H. Sometimes you'll see delta H naught. Okay. Sometimes you'll see delta RH. Sometimes you'll see delta H combustion. Sometimes you'll see delta H fusion. They mean approximately the same. Except for delta H naught is usually done at standard temperature. Okay, so when the value is a negative value, as you guys see here, our delta H is a negative value, that basically means that energy is being released. It's exothermic. When the value is a positive value, as you see down here, that basically means that it is endothermic. That means we're adding energy into the system. So if we take a look at the chemical equation, you can write it this way, where you just have delta H on the side, and you just use that negative to mean it being released. Or you can write it within the equation itself. Both of them are used in chemistry. So if we write it within the equation, that means it's going to be on the reactant side because it's being released. Energy is being released from the system. So then it's going to be on the, on the product side. Product side. Now, if it's endothermic, you're going to have a positive. And then that means that we're putting heat into the system. That means it's going to be on the reactant side. Okay. So as you can see written here. Okay. So you have two ways of writing it. Knowing that, you guys, right? The chemical equation and both formed for this reaction. It says, the thermal decomposition of limestone solid calcium carbonate want to look for it, to lime solid calcium oxide and gaseous carbon dioxide is an endothermic reaction requiring 178 kilojoules per mole of calcium carbonate.
I'm sorry. That's it. That's it. That's it. No. Oh, the chocolate. So chocolate is like a long. The first time I think alcohol. Are you drinking alcohol? I don't. No. Just said open your mouth. Just have to show.
Hey, what did you guys do?
I did that before.
I don't know. It's gonna be important here in a minute. And then we're gonna make okay. What was that? Yeah, that's, you do it out. That would be another way of writing it. Oh, 3. I say. Okay, so let's assume that we have 13 moles of calcium carbonate.
Start doing the
Riley, is it a balanced chemical equation? So we have 13 moles of calcium carbonate. How much energy must we put into it to make this reaction happen? So if that's the case, we have 13 moles. Three. Gabriel, are you paying attention? Guys, are you guys paying attention? Yeah.
Yeah.
So we know that the relationship between calcium carbonate to energy is 78. So then this is 178 kilojoules. Of calcium. So then your answer would be okay. Questions? Piece of cake? Okay, so this is just schematics basically showing you that if you start with energy, you can end up using that to calculate the number of moles and now figure out how much moles of product that you're going to need or that you're going to generate, and then how much energy the product is. So this is just expanding our table. Okay, it says, what is the mass of liquid octane C8H18, a component of gasoline, must be burned to provide 9.05 times 10 to the fourth kilojoules. Delta H equals negative 5,471 kilojoules per moles of octane. What's that? So where did you get, what are you getting? So then I can use my H. know that negatives is just telling us which side of the reaction it's going to be on. So we don't necessarily need the reaction itself. So it's at 5,701 kilojoules. 1 mole. 8 H15. Well, and we're left with moles. So how would I go from moles to mass? What am I going to use? Grams. Now I'm going to figure out the grams. Okay, by the way, so it's molar mass, right? So its molar mass is, you have 8 times 12. It's 18, because 18 times 1, right? So it's 196. 196. That's 18. What was that? 14 grams. 8 H18 mole. Now, sig phase. Okay. Questions? Okay, no questions. I like it when there's no questions. Steve, sometimes you like when there's no questions. What was that? That's why you don't ask the question. Okay, I need a 5-minute break. If that's okay. Solutions. You guys already know about solutions. You know homogeneous and heterogeneous, right?
Yeah.
Okay, so we won't spend a lot of time on that. Okay. We talked about solute versus solvent. Right? So we talked about concentrated versus diluted. Right?
Yeah.
Okay. So saturated solutions. Saturated solutions are basically when you're trying to reach that limit where you can't stick anything else back in there without it starting to fall all out. Okay, that's considered to be saturated. An unsaturated solution is just the opposite of that. It's going to be less than that soluble limit. Okay. Supersaturated. Now, we can make a conditions we can tweak it just enough to allow us to put a little extra in, right? And so when we tweak it just enough to put a little extra in there, it's past that normal limit that we see, but it's still considered to be soluble. But as soon as we make that adjustment, you'll start getting precipitation. Like for instance, a lot of times we will make a supersaturated solution by heating up the temperature. That allows things to kind of go in a little bit more than what it should. And then as soon as you cool it down, you start seeing it fall out of solution. You start seeing precipitation. Solids. Okay. Miscible basically means soluble. Immiscible means insoluble. Okay. This is an example of a supersaturated solution. So this solution was heated up. It's beyond saturation. Now they taken it off the heat. Yeah, they took it off the flame. Yeah, exactly. So now, since they took it off the flame, as soon as they drop a crystal, just a small little crystal, it causes crystallization. Right? You get crystal formation, and then you get these large crystal formations, and you get precipitation of that solute. So have you guys ever made crystals have you bought the little kit to make crystals? That's essentially what it is. You're just basically using supersaturated solution.
That was like 15 years ago.
Sounds fun.
Okay, this is just basically showing you miscible, immiscible. So if I have octane and chloroform, I have them together, right? They're both soluble in each other. So then you can't see any distinction between them. Right? Miscible, here we have a long hydrocarbon chain, and we have water, gasoline, and water, right? Oil and water don't mix, right? Layers. Polarity. So we talked about polarity. That's that concept of a molecule being partially charged. So you have a positive pole and a negative pole, right? So we talked about water often being polar. We've talked about hydrated ions, aqueous ions, where we basically surround the ion by water. So that's like sodium chloride, put it in water, and it dissociates. Now, what happens is it's called a dynamic equilibrium. So basically, these are constantly moving. These are constantly changing. Since it's a dynamic equilibrium, the direction, the movement in one direction is going to be the same as the movement in the other direction. Here's an example of ions dissolving because of polar charges. You can see, we talked about water surrounding chlorine, and then water also surrounding sodium, right? And we talked about that before. Okay, so this is just basically the formation of a saturated solution. So in this case, we have so much extra. So like say if you guys back to say your mom says gargle with warm salty water, and you put a shitload of salt in there, right? And then you have a big old lump of salt at the bottom. Okay, so that's the example of you forming a saturated solution. So you put so much in, right, that you're not able to get any more of it into the solution. There's not enough water to surround all of the salt molecules. That's why that water stays there. And what's happening is that as soon as you get some that goes into solution, some of it's falling out of solution. So of course, it's nice sort of equilibrium going both ways. That equilibrium is going to be consistent. So you're not going to have a net gain or a net loss. Yeah. Okay, so factors that affect solubility. So one of the major factors, have you guys heard warm, salty water? Why do you even want to tell you warm, salty water? You know that cold, salty water will work just as well to gargle and kill that bacteria as warm, salty water. Why warm, salty water? It helps dissolve, so you're actually putting in more salt in solution, right? So the other thing that are going to be another factors are intermolecular forces. Intermolecular forces, or IMFs, it's not the cocktail. Okay, so let's intermolecular forces are those other forces that are involved between molecules. So water and say the sodium ion. So in that case, it's because sodium has a plus charge and water has this bipolar, right? So that means it forms that ion. Okay, another thing is partial pressure. So if you put pressure on a system, you can cause it to actually drop out of solution. So if you take less pressure off the solution, cause it to go back into solution. Okay, so here's an example of intergalactic forces. So this is ethylene glycol. Ethylene glycol is what we use for antifreeze. So if we take ethylene glycol will actually dissolve in water, or it will be soluble in water. You don't see that separation, right? It's visible. So you guys dilute your antifreeze. So you concentrated one and you dilute it to, what is it? It's like 1/5 of the bottle or something like that.
Spitting it as a smoke.
Yes, believe me, dilute your antifreeze because if you use concentrated stuff, it'll blow your radiator. Get it twice. What's
Cut
that?
out.
It actually keeps your.
I don't have to. Do you have that?
Okay, so in the case of oil or hydrocarbon, straight hydrocarbon in water, we know that that one is immiscible, right? We're going to get the separation. And so that's because one is hydrophobic in water. So ethylene glycol would be considered hydrophilic, meaning it likes water. And then oil would be considered hydrophobic. It doesn't like water. So it's unseparate.
We call that, polar as well.
Yes, so it would be polar and non-polar. So if we have a polar molecule, something that's polar, antifreeze is polar, where oil is non-polar. Right? So if you have two non-polar will go together. If you have a polar and a non-polar, they won't. So that's water. That's water. Yeah. Okay, so partial pressure. So in the case of partial pressure, if you release part of that pressure, you're able to get more room for stuff to go into solution. If you put pressure on it, it causes things to start to happen. So here, this is temperature and solubility. So it becomes more soluble as we heat it up. It becomes less soluble as we heat it up. Okay? So this is just basically showing us. So here we have it in warm water, or it was in warm water. It's all soluble in solution. As soon as we move it to ice, it starts forming those nice little solvents. Okay, so when we're talking about solutions or concentrations, we will often use either percent concentration by mass. So in that case, we would take the percent, the mass of the solute over the mass of the solution. Solution meaning both the solute and the solvent, okay, all together. That's what this is just basically showing. Okay, here's an example. If I have 125 grams of solution, it's evaporated to finite, and 42.3 grams of solute was recovered. What is the percent concentration of the solution by mass? So in this case, the solution represents both the solute and the solvent. So that's going to be on the bottom. So that's going to be 125 grams. The solute, 42 point. And then we'll multiply that by 100. That 33. We say fixed. Okay.
But it's like- this is like-
Okay, so when you're preparing a solution, you have to think about the process of preparing. So if you're trying to get it to a certain percentage or a certain concentration, you want to make sure that you go up to that volume. So you're going to go up. Okay. We're not going to do this problem, but I'm going to show you another problem. I want you guys to listen. So you guys can do this on your own. You can kind of look at the notes, kind of get you through it. Polarity. Okay. Polarity is going to be moles of solute over liters of solution. Moles of solute over liters. Okay, you guys already know what moles are. Right? Moles are going to be that quantity. Liters, of course, we know what liters are. So, we're calculating the molarity. You're going to first have to change your solute into moles. Okay. So if we have calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting it to 1.00 times 10 to the second power. So the way that we would do that is first convert 15 grams of sodium hydroxide into moles. So how will we go about doing that? It is definitely not going to. From where? Okay, from our periodic table, right? Okay, so if we look at sodium, sodium is 22 point something. Okay. 40 grams. What's that? Seven. $38. Okay, we're given milliliters, so we have 100 milliliters essentially. So how do I change my milliliters into liters? Times 1,000 or divided by 9. Second. So then the molarity is going to equal the information for molarity. It's going to be moles over liters. So that's going to be 0.1. You mind if I put it up here? So it's hard to- Molarity equals 0.1. 38. Zero point one zero zero. 3.8 molar. Okay. Da-da-da-da. Okay. Okay. Molality is going to be just moles of solute over kilograms of solvent. So here you're comparing to the solvent, not the whole solution. Okay. So how many grams of potassium chloride must be dissolved in 50 times 10 to the second grams of water? We make a 0.400 molality. You guys don't have it?
I'm looking for.
What page is it?
It's probably because I didn't print it out.
Slide what?
Okay. So let me make some
Oh,
copies.
I got it, I found it.
You guys got it? Okay.
Wait, what word?
It's
What's
on
that?
page 22.
It doesn't have the question.
It's after the
It
juice
doesn't have
with
the
the
word
picture.
code.
Oh, we're missing the word problem entirely?
Yeah, it's just the
That's
answer.
the one for 65, it says hydrochloric acid.
For my slide 65, it says milliliters. And it says,
Okay.
yeah, commercial hydrochloric acid. Never mind, I don't have
Okay.
it.
Let's get to that.
Have you considered updating your slides?
Yeah, I have
Smart ass. Don't ask questions.
2 seconds. Do you consider my opinion to myself? Right?
Finish.
No, I'll finish it later. Anyway, yes.
You chose violence today, damn.
Very fine.
So
It's okay.
there, we get a from the publisher, we get images in most cases. And they're images from the books, so we use those images to make the slides. Or
You make them.
I make most of them, not all of them. Some of them were already made, and so I added some along the way. And I've taken some out because, let's say, for instance, this chapter here, I wanted to put chapter 16 with chapter 10 because it's important.
Thank you.
All the time. I don't have enough space.
When you start teaching the class, you can, okay? But I'll take your suggestion into consideration. As soon
Yeah,
as you
next
start
week you
teaching the
get to
class,
teach.
don't worry about it. Next week, on Monday, you get to teach the class.
Hey,
Okay.
hooray.
Okay, so, in this case, since we know that
Be
molality
grateful you don't have to work.
Guys do what?
is gonna equal
I like sleep too, though.
moles
It's the money I have.
over kilograms, right?
That's true.
So then the first thing that we want to do, we know that water is going to be our solvent. So we need to change this into kilograms, right? So how would I change grams into kilograms? What's that? Divided by 1,000. So we know that this is going to equal 0.400. So we just plug this in for our 0.250 kilograms. So then we solve for moles. 0.4 times 0.25 kilograms. Okay, potassium chloride. So how would I get the mass of our potassium chloride? Potassium weighs how much? Okay, 39, and chloride weighs how much? Okay, so then 39 plus 35.45. That's 74 times 4.5. Four, 4.5 grams. Yeah. So there. 7.4 5 exact.
So you never forget.
Totally get more. Wow.
Okay. Questions?
I'm gonna fuck you up if you say that one more
What's that?
time, Gabriel. I'm not playing with you. Say a mold one more time.
Is it 3
It is 3 sig figs.
I was struggling.
7.44. How many numbers are there?
So fuck yourself, you little Dorothy Explorer.
There's 3, right? No, you always count all of the numbers that are there. So, yeah, 0 there, that's 0. Yes.
What is the second conversion factor say? When 400 moles, is that 1 kg water?
Here? Right here? Where you make a reference?
I wrote it differently. It's written differently on
Okay, so we know that this here is 0.04 moles, so molality, that's it. That loop and moles over kg. No, it's saying that I have 0.1. Oh, down here, yeah, it's 1 kg, yes, 1 kg. It's understood to be 1. Yeah, so that little m is the same thing as saying moles over kg of water. So that's what it means. Does that make sense? Okay. Yes. Okay, so these are the ones that you're going to need to be concerned with. So it's going to be percent, it's going to be molarity and molality. So don't worry about that.
That slide's not in my notes.
Let me print it out.
Thank you.
Maybe it's just that.
Anyway.
I lied, I have it.
So it's just on a different page.
Oh, so you mean to say.
I don't know what happened. So anyway, so when you're doing dilutions, you're going to basically use V times M. It's going to equal V. So your concentrate, your V concentrated times your molarity concentrate is going to equal your V dilute times molarity dilute. Another way of thinking about it is C1 V1 equals C2 V2, where all of those things that we talked about, that percent, that molality, that molarity, all of those represent concentrations. Okay, so C means concentration 1 times volume 1 is going to equal C2, concentration 2 over volume 2. So if you just kind of use this equation, you can dilute from anything. So in other words, you're starting with something that's concentrated and then dilute down to something that's dilute. So let me give you an example. Let's say we have a 5 molar sodium chloride solution. And we have 50 mils of it. How much of a 0.5 molar solution can I make? So if you let C1 equal your concentration That 5 molar. Your C2. gonna equal 0.5. Your V1 is gonna be 15 mil. Then your V2 is gonna be what we're looking for. So then you just solve this for V2. So you solve for V2. Y, V1 over C2. So we get 5 molar. Moles over 0.5. Okay. So if you're making a solution, the first thing that you want to do, we're going to use, let's say, volumetric. So we're going to make 1,000 mils of a 1 liter volume of our solution. So what you're going to do is you're going to put in a small amount, and then you're going to bring it up to a volume of 1,000. So your first instinct as a student when you make solutions is, it says I need 1,000 mils. So you may have something already in there, right? You want to bring that up to 1,000 mils. Most people, what they do, their first instinct is they'll measure out 1,000 mils, right? And they'll pour directly in. And then so your volume is going to be greater than what it should be, because it's only supposed to be 1,000 mils of solution. Because when we're talking about that concentration, it's talking about the solution of molarity and concentration. Because it's the percent concentration of the solution. Right? So keep that in mind, because I guarantee you're going to have questions. Either a written test, also a multiple guess test. Okay, so how many mils of commercial hypochloric acid, which is 11.6 molar, should be used to prepare 5.50 liters of 0.5 molar hydrochloric? Okay, what am I going to use? What's that? What equation? Six molar. Sure. That's 0, 0 molar. Zero point 37 liters. I convert that to milliliters by
5,000.
okay. Questions? Questions? Concerns? Okay. So this works for stoichiometry as well. So but the first step is that you have molarity and you have volume, you're able to get the number of moles. And then once you get the number of moles, you can use that to sit there and calculate the moles of or the other reactant. So here is my last example for today, and that's what you guys know. Okay, so this is calculate the volume in milliliters of 0.84 moles of sodium hydroxide required to precipitate as copper 2 hydroxide, all of the copper ions in 30 mils of 0.635 molar copper. So the very first thing that we want to do is to do what? We want to write down the chemical equation. That's right. Okay, so what are our reactants? Sodium hydroxide. Plus copper. Copper 2 sulfate. Okay, now the fact that we have milliliters should be a dead giveaway. It's a solid, liquid, gas, or aces. It's aqueous. And then sodium hydroxide. We have milliliters. It should be what? Aqueous. And then that's going to make copper 2 hydroxide. What is the chemical formula for copper 2 hydroxide? Somebody say 2. Okay, and we know that that's a precipitant, so I'm going to put what by it? Plus Na2. That is correct. Good job. Okay, is it balanced? What do I need to do? Right there. Then we're good. That'd be 2, 2, 2, 2. Okay. 2 hydroxides, 2 sodiums. Okay, so we have it balanced. Okay. So we know that we're starting out with 30 mils, 0.65. So we can get the number of mils. So we start off with our 30 mils, we have to change our mils into liters. Let's change our milliliters to liters. So, we know the concentration, which is moles per liter. So we put 6 moles over 1 liter. Copper 2 sulfate. Well, liters are going to cancel out. And we're left with just moles. So if we know that we have this many moles, this type of moles of copper 2 sulfate, I can use my chemical equation to figure out how much moles of my sodium hydroxide I'm going to need. So what is the relationship between copper 2 sulfate to sodium hydroxide? It's here and what's here? Okay, so for every 1 mole. Because all the other ones before it were not chemical reactions. This is a chemical reaction. Question? Okay. So again, this allows us to have moles of sodium hydroxide.
Actual cake. Some chopstick.
Zero, 0.038.
Maybe. If it's cheesecake,
Sweet.
listen, here's the thing.
And I didn't want to eat those. So it was like, I don't want to eat those. So I was like, yo, I don't know you do this one.
Take them.
Do it. No one ate.
Okay. So then if we wanted to calculate the volume,
Unless you guys have
we can use our
Did you guys have ice cream?
and moles. So then we have 0.0. Are you guys paying attention? Yes. Harder. Okay, so I have 0.842 moles bottom for 1 liter on top. They want milliliters, so then I need to change my 1 liter, 1,000 milliliters. Okay. Questions? Okay, so you will definitely see this on your exam. The take-home exam, you'll definitely see it on your final. Yes.
So we just like.
Yes, you're gonna turn in your exam. You're gonna upload it. That is your actual take-home exam. You get to work on it at home. Because I want to do that take-home exam.
What does this one do? The take home exam?
The take-home exam is due next Wednesday. Final exam.
That's the last big one?
That is the last day of class, yes. Right?
Yeah.
I'll miss you. I'll miss you.
Day for sure.
Wednesday
Maybe
for
we'll have a
lab.
beer.
I'll see you Monday for presentation.
We have lab on Wednesday.